Hi everyone. Today we're going to talk really quickly about doing regressions in Excel, do an example of a multiple regression model or ordinary least squares, and just give a quick overview and a quick introduction into doing regressions and how to use it in Excel. Right? Certainly this goes a lot more complex than we're going to get into today. We could spend a whole semester talking about doing regressions and the theory that underlies it and the mathematical computations that underlie it. Nevertheless, regressions is useful when making predictions and predicting outcomes and making assessments and inferential statistics and using the data to make statements about sample data, make inferences towards population parameters, essentially. So we're going to briefly talk about introducing this type of statistical practice modeling technique and predictions. Correlations can be used to predict the value of one variable from the value of another. So we've talked about the Pearson's product moment correlation coefficient, the Pearson's R, which makes a prediction between two variables, right? It says if one variable has an effect on another. If ice cream sales increases crime, right? If delinquent peers increase delinquent involvement. So predictions attempt to estimate future outcomes based on present ones or past ones or previous ones. We take known data, empirical evidence, and apply statistical methods to make assertions about that data and inferences and perhaps predict potential outcomes, even forecast with some of these statistical techniques. So we've discussed the correlation coefficients and the Pearson's R. Now we're just taking a step further to integrate multiple variables into the analysis. So now regressions as a whole is a set of statistical processes for estimating the relationships among variables. There's a lot of procedures that are involved when you talk about regression analysis. You need to know the assumptions of each model and try not to violate that. And I'll get to that in a second, in a little bit. But examines the value of a dependent variable, how it changes with respect to independent variables. Like I said before, how ice cream sales affect delinquency, right? Or delinquent pairs affect delinquent activity. So there's different models that fall under this domain of this analysis. Certainly ordinary least squares is what we're going to talk about. That's the idea of multiple regressions or linear regressions. It's really what it is ordinary least squares. And there's also logistic regression models, Tobit, negative binomial, and all of it really is based on a general linear model. Now, in all simplicity, what all this is how the dependent variable is measured, okay? So we're going to look at ordinary least squares, and here the assumption is that the dependent variable is continuous. It's a continuous measure, either a ratio or greater level. You can't have a nominal level variable, or even an ordinal might be a violation of that assumption. But logistic regression is good for nominal variables, like a yes/no type of question. Did you recidivate? Yes or no? 0 or 1, and that's your dependent variable, right? Did this treatment have an effect on this type of recidivating outcome, right? Ordinary least squares. So if you want to look at how this treatment affects the number of times somebody uses marijuana in the year following treatment, that would be a continuous variable, something that's greater, right? And it's not limited. And these other ones get at skewed data when the dependent variables tend to be highly skewed, but the general linear model underlies it all. So that being said, this is essentially what it looks like. You're looking for a regression line, essentially, when you're doing a regression model. And I'm trying to give you a quick picture of how it looks. So you have a data set here, and this would be your independent variable, and this would be your dependent variable. So let's say ice cream sales has an effect on crime. I know that's not true, and it's based on, there's other factors that need to be accounted for, but I'm using that example. Let's say delinquent peers has an effect on delinquent involvement. The number of hours you spend with your delinquent friends, or the number of friends that you have that are delinquent based on percentage perhaps, and the likelihood that you're involved in delinquency. See how it naturally trends. The reports tend to trend. So if people have 100% delinquent peers, all their friends are delinquent, then there's a high likelihood of delinquency. A lot of delinquent activities that are occurring. If they have 0 delinquent peers, well, they're around 0 delinquent involvement. And that makes sense. If all your friends are smoking weed, then they're probably smoking weed as well, right? So hopefully that makes logical sense. That's just kind of how it looks from a picture perspective. So what the regression model does, it attempts to fit a line. It attempts to fit a line between the data. A line of best fit essentially is what it's doing. So you have your observed values and then the predicted values. So this is where predictions come into play, right? And then you can see how observed values deviate from that line. And all this deviation that exists here, you know, this is the error. This is error for each line, and there's a cumulative error that exists. And that's because predictions aren't necessarily perfect, right? Predictions, especially within the social science, things aren't going to exist 100% of the times, right? Some people might have a lot of delinquent peers, but have no delinquent involvement. And, you know, some people might have a lot of non-delinquent peers and be highly delinquent. So hopefully that makes sense. So these are just making predictions, and it's based on this line. So it minimizes the line of best fit. The regression line minimizes the distance between each individual prediction point, predicted point, and the regression line. So what you're trying to do, you could take the average. You could say, well, the kids in 12th grade commit this delinquent, smoke weed on average this many times. Well, you're not necessarily accounting for other factors might influence that, right? School climate, if they've dropped out, if their friends are delinquent, and all these other factors that might need to be accounted for. So instead of just using that average, you can expand upon it and say, well, there's other causes that are underlying this average, that are manipulating this average. Some pull it high, some pull it low, right? So the distance between each data point on the regression line is the error in prediction. So this distance is the error in each prediction. And you can calculate that. And this week's module, I believe I have y'all calculating each value and how far it deviates from, okay? So written out, this is kind of the regression equation. You have your dependent variable, this is the value of the dependent variable. It equals the intercept plus the independent variable with this population slope or coefficient, and plus the error. This is a bivariate regression model. Now, moving forward into an example that we're about to work through, we kind of talk about bivariate regression analysis as 2 variables. That's Pearson's correlation coefficient, essentially. It's essentially going to achieve the same types of value and the t-test and the if functions and all that stuff that underlie it. But the multiple regression model incorporates multiple independent variables. So let's say that marijuana use, this is how it would look. This is how the previous equation would look. Marijuana use would equal the intercept. This would be the value of marijuana use, plus the slope of delinquent peers times the slope of delinquent peers, so plus the error. I'm sorry, I chopped it up. Multiple regressions includes multiple variables, so this would be an equation, and this will make sense because we're going to walk through it, and then we're going to talk about the results real quick. Okay, so I have a data set here for delinquent peers, sexual activity, age, and marijuana rate. Okay, this would be our dependent variable. The marijuana use would be our dependent variable. So if we want to do it, a regression analysis within Excel, a multiple regression analysis, we go to the data analysis, click the regression tab. So our input Y range, Y is the dependent variable, X is the independent variables, okay? So our Y range, we're going to look at marijuana rate. We're going to look at how delinquent peers, sexual activity, and age influence marijuana use. So our X range, we'll click these 3 variables and highlight them and drag them down. So those are our 3 variables there. So we're going to put our confidence interval at 95%, so less than 5 times out of 100. We'll put our output range right here. That's where we're going to get our values at. We're going to include labels because I highlighted over that stuff. And I'm going to do a line fit plot, okay? So we can plot it out, and I can kind of give you another graphic that we looked at, the line of best fit, essentially. All right, and then I'll just click OK, and hopefully those results calculate really quickly. So this this is your output. Now this is, and we're going to walk through this stuff step by step. So our dependent variable was marijuana rate, and we're looking at the effects of delinquent peers, sexual activity, and age on marijuana use, essentially. Okay. First and foremost, you want to look at your R-squared. This is the amount of explained variance, and I'm going to interpretate this a little bit more in a little bit. The F value suggests that since it's a significant value, suggests that at least one of the slopes in the regression model is not equal to 0. Okay, so it perhaps has a significant effect. Okay, is an adequate explanation for it. So these are your three variables that we looked at, the three independent variables. In our intercept, this is the dependent variable. This is marijuana rate. So here we can see that delinquent peers has a coefficient value of 2.75. This is a standard error. And this is our T statistic, which is statistically significant. Okay. Sexual activity doesn't have a statistically significant effect on marijuana use based on this sample data, and age doesn't have a statistically significant effect on marijuana use either. But we do know that delinquent peers has an exceptional effect on it. All right. Now, since we clicked on the line plots, we can kind of see, see the trends in the data. So the other two independent variables we assessed, sexual activity and age, they didn't have a significant effect, and you don't see any real trends in the data. But if you look at delinquent peers here, you do see a trend that it tends to exist. Okay, here you can put a trend line in it, do the predicted marijuana rate, and hopefully y'all can see that. So the blue values are the observed values, okay, that were assessed. The orange ones are the predicted values for each domain. And as you can see, there's a trend that exists. Now, if we look at age, and that is statistically significant, and we're going to interpretate it even more. But if we look at age, there is nothing. Everything's really jumbled up all over the place, so it doesn't necessarily have a significant effect. So this is a multiple linear regression model, and now we're going to interpret the results. Okay, so order of interpretation for looking at a regression model or a multiple regression model, you should look at the R-squared, the F-test, and each coefficient independently, because you can make statements about each one. This isn't necessarily open to question. This data set is actually a legit data set that you can achieve on the internet off the National Youth Survey. So these are real results. They're not manufactured in any way. But anyways, we're going to talk about the R-squared, the F-test, and one of the coefficients, because there's time limitations based on this video if y'all are still watching. So the R-squared value. Now, the R-squared value is 0.793, suggests that approximately 79% of the total variation in marijuana use is explained by using regression model, by using this line. So instead of using, as opposed to just the mean for marijuana use, prediction errors can be reduced by up to 79.3% when using the regression lines as opposed to the mean of marijuana use. And hopefully that makes sense. If instead of just saying, well, kids on average use marijuana at this rate, you can reduce that. You can reduce that by saying, well, we factored in the influence of delinquent peers, the influence of age, the influence of sexual activity, right? Sexual involvement as a juvenile. And we see that by doing so, we can reduce prediction errors by 79.3% when using the regression line, when using this regression analysis. We could have factored other independent variables that might have influenced, right? Two-parent household, socioeconomic status, if they dropped out of school, prior arrest history, all these things might influence the rate as well, right? And they might have significant effects on marijuana use as well. Okay, so this is what it looked like before. This is the results from the Excel file. So the R-squared was up here, and this is the value. So 79.3% of the total variation is explained by using the OLS regression model. Okay. Next one, we're moving on to the F-test. The F-test, this is the F statistic right here. We've done F-test before when we did ANOVAs, and it's the same type of test, and it applies over. The f-test estimates an f-value of 33.178, which is statistically significant. Because the f-value occurs less than 5 times out of 100, the null hypothesis, this is why we talked about null hypothesis and hypothesis. The null hypothesis can be rejected, and one can conclude that at least one of the independent variables, age, sex, sexual activity, or peer delinquency, does not have a zero effect on marijuana, all right? Can't necessarily say one of them has a significant effect because all of them might be 0.051 and they don't necessarily have a statistically significant effect, but they're very close. But the f-test would indicate that. But what you can say is that at least one of the independent variables doesn't have a zero effect on marijuana, right? When looking at all things together, this is a holistic test. This is an f-test. This is accounting for all these factors and all the variation between all the variables in one model. All right, so we see the f-test here. I didn't include the p-value, which it does have over here, and it's an exponentiated value like it is for delinquent peers. But that's the value, and that's the interpretation. That's a concise and perfect interpretation. So the constant, this is the intercept here, okay? It's marijuana use. This is the dependent variable. This is we're looking at the outcome, all right? So the constant is marijuana use, or it's the intercept. So usually this value isn't necessarily that interesting, worth interpreting, because we're seeing how things affect the constant or affect the intercept. But the estimated coefficient value for the constant, or marijuana use, is 3.417, which is the expected marijuana use rate for the regression line when all the independent variables in the model are equal to 0. So this is it. This is 3.417, right? And that's a perfect interpretation of how you would interpret marijuana use without any subjective involvement. You don't necessarily need to say it's significant or not. It doesn't necessarily matter because that is the value. That's the expected marijuana use value when delinquent peers is at 0, when sexual activity is at 0, when age is at 0, okay? And all that stuff isn't necessarily realistic, especially since age is at 0. If we didn't have age in the model, 0 and 0 intercept would mean something. But still, it does mean something in and of its own right. When all these factors are at 0, this is the expected marijuana use, okay? Within this sample, all right? So the independent variable, and we're going to just look at delinquent peers, okay? This value. And we're going to assess and just interpret this real quick. Independent variable, delinquent peers, this is an unstandardized coefficient value. That's what Excel gives you. We've talked about the differences between standardized and understandardized and putting things on the same metric. So all this stuff comes together, all right? So the unstandardized coefficient value for delinquent peers is 2.755. For every 1 unit increase in peer delinquency, one would expect an average of 2.755 increase in marijuana use when controlling for the other variables in the model. All right, so for every 1 unit increase, when you see an increase in X, say this is a 1 unit increase, 20 to 40. This isn't necessarily that, but for every 1 unit increase, we would expect Y value to increase, and you can see that it trends up like that. And if we go back to the actual data itself, we can see that here. So for every 1 unit increase that exists here, we see the value of Y increase, okay? And hopefully that stuff makes sense. Where am I? Okay, and so we would, for every 1 unit increase in peer delinquency, one would expect an average increase of 2.755 increase in marijuana use while controlling for the other variables in the model. This is while the other variables are at 0. Okay, when these variables are held to 0, we would expect this thing to increase, marijuana use to increase by 2.755 for each 1 unit increase. So the coefficient value corresponds to a t-statistic value which lies in the critical region. Therefore, one would reject the null hypothesis and conclude at the 0.05 level of statistical significance that peer delinquency has a statistically significant effect on marijuana use when controlling for the other variables in the model. All right, this value is on average, and predictions aren't always perfect because there is error. There's error involved, and that's what the standard error is here. And we could interpret it even further and include that, but this is a perfect interpretation of that coefficient. So it is statistically significant, and we say that here. Peer delinquency has a statistically significant effect on marijuana use. So we rejected the null hypothesis. If it didn't have it, we would fail to reject the null hypothesis and conclude that it does not have a statistically significant effect on marijuana use. So sexual activity and age, you would say that. You would say the inverse of it, okay? So in the end, this is kind of what the equation looks like. So marijuana use, we've interpreted intercept. This is the value, the expected marijuana use value when all these factors are 0, when age is 0, when sexual activity is 0, and when delinquent peers is 0. All this would be multiplied by 0, right? And that would be the expected marijuana use when those things are at 0, and that's our intercept value, right? So delinquent peers, 2.75, we can see that here. Sexual activity, 0.15, and age, this is minus 0.25, right? It's the decrease with age in the sample for whatever reason. So, and then the standard error, this is your standard error. So that's essentially it. This is essentially all we're going to talk about today as far as doing multiple regressions, understanding how the process is done, doing the interpretations. You need to understand the assumptions as well, a little bit about the assumptions before you go violate the assumptions of the statistical procedure. You need to have a continuous dependent variable. Your error terms need to be normally distributed, and it has to have a lot of different assumptions. The big assumption that is violated is the dependent variable not being a continuous measure, okay? That's what other statistical models are used for, and we're not necessarily going to get into that or detail that or do examples with that, but and you need more advanced statistical packages to do that type of analysis. But it is possible, and it is achievable, and this is certainly achievable within Excel, all right? So hopefully this is helpful to y'all, and you know, good luck with everything. So y'all take care, okay?